So I'm going to go through first description of concentrically braced frames. We will talk about key behavior of concentrically braced frames and some of the underlying principles that are used in the design provisions, and then we will look at the AISC seismic provisions for concentrically braced frames. And then I will highlight, if there's time, I will highlight some recent research that's been going on here with myself and my colleagues at the University of Washington, looking at performance and economy of special concentrically braced frames. And if there's not time, those slides are included at the end of your handouts if I don't kind of get to that fourth bullet. Okay, so I'm going to highlight, as we go through, I'm going to highlight where research has really contributed to the state of practice for special concentrically braced frames. And in particular, I'll highlight that there's some notable changes that happened for the 2022 AISC seismic provisions that were a result of a significant research project conducted at the University of Washington with funding provided by National Science Foundation and AISC that was conducted by Charles Roeder, Don Lehman, and myself here. And then there's some figures kind of throughout that are borrowed from the AISC's Teaching the Seismic Design Provisions that were published a number of years ago, and I have been kind of consistently updating those, but some of the underlying figures were originally from that set of slides that was put together by Mike Engelhardt from UT Austin. Okay, so for seismic design of concentrically braced frames, we need to first understand the underlying objective of the building code. That is to prevent collapse in the extreme earthquakes that are likely to occur at the site of the building we are designing. The objectives of the building code are not to limit damage, maintain function, provide for easy repair. It is implied that by designing for collapse prevention in the maximum considered earthquake, these very long return period earthquakes, that when the shaking is less than maximum considered earthquake shaking, that we would get better performance than just collapse prevention. However, we do nothing in the building code to specifically design for performance states other than collapse prevention in the maximum considered earthquake. So how do we do that? Well, we do that in steel structures and actually all the structures that are in the building code by utilizing inelastic deformation capacity of the structural systems that we are designing. That's illustrated really simply here with this moment frame that has a lateral load. That's kind of what the earthquake is doing to the building. You have mass times acceleration at the floor levels. And that lateral load is imposing a displacement. And in earthquakes, we expect the displacements to be substantial enough to cause inelastic behavior of the structure. In other words, there's the nonlinear relationship between H and delta. So we're pushing these structures out to large enough deformations that the linear relationship between H and delta is no longer true. And we have inelastic behavior, and that inelastic behavior is generated by a number of mechanisms within the structure, including yielding, buckling, and other things that we will talk about as we go along. So what has traditionally been done is we can define a ductility factor mu, that is the displacement at which a structure fails or collapses, divided by the kind of proportional limit, the displacement at which the load is no longer proportional to the displacement, the yield displacement. And we can define this ductility factor as such. And then the kind of underlying principle of the building code is that we can design structures that have more deformation capacity, in other words, more ductility, more displacement, so larger values of this ductility factor, larger ratios of the displacement at failure to the displacement at yield, we can design structures that have larger ductility capacities for smaller earthquake forces. And this is generated, the building code, what it does is it employs what is called the equal displacement hypothesis. This has been around for a long time, and the general idea is that if you take a simple system here that is elastic, put the pointer out here, so that responds elastically in an earthquake, and you generate a force, maximum force called H elastic in this figure, and it goes, and then the structure deforms to a displacement of delta max. If you were to take that same structure and instead of making it just linear elastic, you were to make it, say, have a bilinear behavior where it yields at, say, 1/4 of H elastic and then has this, inelastic behavior that's idealized here as elastic perfectly plastic, you would, for a set of earthquakes, as long as those structures have the same initial period, the same initial stiffness here, for a set of earthquakes, on average, the displacement demand for the inelastic system, the system that yields at 1/4 H elastic, and the elastic system, the structure that remains completely elastic, those displacement demands are roughly the same. Okay, and this was observed, again, early on in the 50s and 60s.